Thank you. This is a great opportunity for our relatively new group to advertise our work. So I'm going to talk about, first, give a very experimentalist explanation of quantum metric, which I think for many experimentalists is a very abstract concept. And then also nonlinear or nonlinear Hall effect, and then I'll talk about our data. But before that, I'd like to start from something even more relevant for the real world. So we know that in our environment there are a lot of microwave energies. These can come from our cell phones. It could also come from thermal. So one of the motivations of energy industry is whether we can build something called an ambient energy harvester that basically take this energy and transform it into a DC electricity, right? So then you can imagine you have something, a wireless charger, which we already have. And in this work, basically, the ultimate kind of application that I can sort of advertise is that we're going to try to understand or explain how an antiferromagnet, and particularly the antiferromagnetic spins or the antimagnetic order, is relevant for this kind of energy harvesting. Okay? And talking about this, it is obviously a nonlinear effect because you convert AC electromagnetic waves into DC electricity, and we know that, like I said, we already have a wireless charger, and those are based on what we have every day, which is p-n junction. And these can serve as wireless charger, no problem, also solar cells, stuff like that. But there are some limitations from the application point of view. For instance, if you look at the rectification efficiency as a function of the power, the intensity of your wireless signal, then you realize that we have very, very efficient rectifier when the wireless signal is sufficiently strong. But when the wireless signal is very weak, they become very inefficient, and that's understandable because those are semiconductors. So you need the electric field of your microwave to be strong enough to overcome the band gap. Okay? And similarly, when the frequency of the wireless is much higher than a few gigahertz, then those silicon or semiconductor-based rectifiers become inefficient. And that's also understandable because in these materials, basically, the electromagnetic wave shakes the electrons, so it depends on the mobility of your silicon. So when the silicon cannot move as fast as your wave, then it becomes very inefficient. Okay? So that actually is one of the, well, obviously they're mostly fundamental motivation, but one of the application motivation for studying so-called intrinsic diode effect. So what do I mean by that is, if we look at a p-n junction and look at a ferroelectric or non-central symmetric conductor, then we immediately realize that they are very similar in the sense that both of them have a non-central symmetric charge distribution, right? So then it's not really surprising. And recently, there are many studies of this kind of non-reciprocal or nonlinear transport in those non-central symmetric conductors such as WTE2, tantalum arsenide, but also more recently, this is even generalized to superconductors called the superconducting diode effect. Okay? Now, like I said, if we try to summarize, then both of these come from the charge degree of freedom. And then we can, what we want to ask is that what if we have an antiferromagnet, right? So if this is just a bilayer, okay? And if I remove the spin, look at the lattice, then this is perfectly, or look at the charge, this is perfectly central symmetric. But because the two layers have opposite spin, because of the antiferromagnetic order, the spin actually breaks inversion symmetry. So for some of your experts, it is also called PT-symmetric antiferromagnet. Okay, so basically, then we want to ask: can these kind of a PT-symmetric antiferromagnet lead to nonlinear rectification effect? Okay, and it turns out that this is possible, and also from the fundamental point of view, it's actually coming from a very fundamental geometrical property called quantum metric. And I think we are all quite familiar with the concept of Berry curvature, and especially it's become very important through the study of the intrinsic anomalous Hall effect, and later on various types of intrinsic, spin Hall, valley Hall, etc. But actually, if we look at the Bloch wave function, because the wave function is a quantum property, is a complex mathematical structure, it turns out that if you try to study its geometric, and you can define the so-called quantum geometric tensor, actually the Berry curvature is only 1/2. It's only the imaginary part. There is also a real part, which is called the quantum metric. And I give you the formula here. This is the Bloch state and some derivatives. And you can see that basically, really, they're just the imaginary and the real part. So basically here, we want to show that actually this quantum metric can also lead to an intrinsic anomalous Hall effect. But it's actually in the second order, and it's in the antiferromagnetic. Okay? So and now, before I kind of go to show the result, I also want to say, okay, so this is quite abstract. So then can we, for experimentalists, have some sort of kind of understanding or sense of what actually is a quantum metric? Like I said, actually I didn't say that, but the quantum metric is basically the distance between nearby wave functions in K-space. So what do I mean by that? This can be simply shown by, let's say, it's just an example, it can be anything, but let's say here I have a one-dimensional lattice with 2 orbitals. So then basically I will have 2 bands, conduction and valence. And let's say I basically focus on the conduction band, then I have a Bloch wave function at gamma point, and I have a Bloch wave function slightly next to the gamma point. So basically, G, the quantum metric at the gamma point, is really defined by the distance, or basically the difference if you subtract these two. Okay? So this is still quite abstract, at least for me as an experimentalist. So let me try to give a more intuitive picture, hopefully. So I'm going to continue with this one-dimensional lattice. So imagine that now we have these 2 bands. Now basically the Bloch wave function as a quantum wave function inside the unit cell has 2 choices. Has a choice of either purely occupying the alpha orbital or purely occupying the beta orbital, or some quantum superposition of alpha and beta. It's like a qubit 2-level system, okay? At a particular k, right? So then a trivial quantum metric can be easily visualized in an atomic insulator where the entire conduction band comes from the alpha orbital and the entire valence band comes from the beta orbital. Then let's just use the definition we have. Basically, then we can map, like I said, the 2-level system, so we can have a Bloch sphere and define the purely alpha as the north pole and the purely beta as the south pole, and then the superposition as a generic point on the Bloch sphere, right? So then basically in this atomic insulator, we know that if I try to map this gamma point wave function, then I know that it's coming from the alpha. If I try to map the next wave function, then it's also coming from alpha. Therefore, the distance is not the distance in K-space, because obviously there's a distance in K-space, but that's not quantum metric, what quantum metric is. The distance is the distance on the Bloch sphere. And we see that in an atomic insulator, this is 0, so the quantum metric is purely trivial, okay? Now, what about let's say a topological insulator where these 2 have actually a band inversion? Then basically you can imagine that actually, the orbital will be quickly, content will be quickly changing, right? So now, if we do the same analysis, the gamma point is still purely alpha, but if I move to the next one, you can see that it's some sort of superposition of alpha and beta. So then this is actually moving toward the south pole, but some generic point, right? So therefore, this quantum metric is basically the distance. So it basically tells you how fast the wave function component, or the one-near orbital, I think that's what the theorists mean. That's what I understood. So change as I move in K-space. Yeah, how fast does it change? So, okay, so this is kind of the meaning of the distance. Then why is it relevant, right? It still seems to be very kind of abstract. So let me give you a I would say not rigorous, but intuitive argument from the experimental point of view, okay? So imagine that I'm applying injecting a current or applying an electric field in a conductor, right? So basically, I'm accelerating the wave packet from k to k plus delta k, okay? Let's imagine k is the gamma point, k plus delta k is the next point, right? But we just said that at the gamma point, the wave function is purely localized at the alpha, whereas at the next point, it's already some mixture, which means that it's in between alpha and beta, right? So that means that the very act of me accelerating the k, change the k, will lead to a spontaneous current because the wave function needs to shift in my unit cell from the alpha toward the median point, okay? So that's a sort of an intuitive argument why this kind of quantum metric information will lead to a current, okay? Okay, so now let me go to the specific predictions. So basically, we all know that these intrinsic anomalous Hall effect in ferromagnets. So basically, in this case, the sample has a non-zero magnetization and also has a non-zero Bayer curvature, and the Hall effect comes from the so-called anomalous velocity, the transverse velocity. So this is basically omega cross E. So this is the classical. So what we are interested in this PT symmetric antiferromagnet, and in particular, this PT symmetry actually forbids the sample to have any Bayer curvature omega and any net magnetization. Okay, so therefore there's no linear, the classical intrinsic anomalous Hall effect. But this system still has non-trivial Bayer curvature, and the theoretical prediction is that actually this G will lead to a anomalous velocity or anomalous Hall effect. But you can see that whereas here this is linearly proportional to the electric field, here is quadratic, and it's also proportional to the G of the electronic system. So that's the quantum metric nonlinear Hall effect that was predicted very recently, okay? And we saw this proposal, and we thought this is very, very interesting. So we were thinking what kind of material this could be good for. So then we turn to, we are studying this manganese bismuth telluride 124. And basically, this is a van der Waals layered structure. This is one unit cell, and then a van der Waals gap, and the next unit cell, okay? And then at low temperature, it indeed have this layered antiferromagnetic order, intrinsic order, 25 Kelvin. So therefore, you can imagine if you exfoliate, then basically the net magnetic moment will depend on the odd or evenness of the layer, and also the topology in correspondence depend on the odd even. So odd layer, there's net magnetic moment like a ferromagnet, and this is predicted to be a quantum anomalous Hall insulator, whereas even layer, there's no net magnetization. This is a PT symmetric antiferromagnet, like I talked about, and it's actually also predicted to be an axion insulator. But for the quantum metric nonlinear Hall, this topology, axion topology is not really important. We just need it to have a large quantum metric and to be PT symmetric, okay? But there's still a, okay, good. But there's still a kind of, this material seems to be very nice, right? So it's a topological, so supposedly there is a very large quantum metric. The symmetry, PT symmetry, is also correct. There's still one condition that was not satisfied from the theoretical proposal, which is the proposal requires the material, if you think about the 2D material, to don't have any outer plane rotational axis. And for the triangular lattice of MBT, we know that there is a threefold rotational axis. So therefore, what we did is we used this heterostructure technique. We actually built a sandwich where the even layer, let's say 6-layer, 4-layer, MBT is in the middle, but on the two sides, we have black phosphorus. And this black phosphorus is an anisotropic material that do not have a threefold rotational symmetry. So therefore, by stacking them, we break the rotational symmetry of this heterostructure. So the first thing that we did is then to check, indeed, in this heterostructure, the threefold rotational symmetry is broken. You can either check that by measuring the angular resolve, the electrical resistivity, You can also check it by just room temperature second harmonic optical second harmonic generation. So in the electrical one, basically the conductivity is completely isotropic because of the C3. But once you break C3, you see a prominent twofold symmetry. And for the SAG, you see this nice flower six-fold pattern indicating the threefold symmetry. And once you have the interface, then the flower is distorted. So we show that indeed the threefold is broken. So then we take these system and we measure the nonlinear Hall. And the nonlinear Hall, the most easiest way to measure is basically in the low frequency, like tens of hertz or hundreds of hertz. You flow a current of I omega, and you measure the transverse voltage, but you measure it at the frequency of 2 omega. So let's say 10 hertz, then you measure at 20 hertz. You can easily do that by a lock-in amplifier. So this is what we found. Indeed, we found a quite prominent Hall effect that is quadratically to the incident current. Okay. So now I'm going to show you a few interesting properties of this nonlinear Hall effect. First of all, I'm going to show you how it is relevant to the antiferromagnetism. Like I said, because now I have an order parameter, so there are two equivalent degenerate antiferromagnetic state. First layer down, second layer up, or vice versa. First layer up, second layer down. So we can actually use a E dot B field. I'm happy to explain more, but just for now, just simply we can use some experimental protocol to prepare the sample into majority of one state over the other one. And then once we prepare, we measure the kind of the response, right? So if we measure just the simple Joule conductivity or Joule resistance voltage, then it's Ohm's law, and you can see that the two domains have the same resistivity. But when we measure the nonlinear Hall effect, we can clearly see that actually this nonlinear Hall effect is actually controlled by the antiferromagnetic order. Okay, and that means that if we actually measure as a function of temperature, then basically this is a unique response of the antiferromagnetic order. Above the nil temperature, it vanishes. Okay, and another interesting aspect is that this is theoretically predicted. You can in the anomalous Hall community, you can look at this so-called scaling, right, to look at whether the anomalous Hall is independent of scattering time, which some people refer to as a dissipationless, or it's it's dependent on the scattering time. So you can do that by varying temperature. Then your sigma xx, the Joule conductivity, which is proportional to tau, will change, and as a result, you can measure the scaling. So we see that actually this nonlinear Hall effect is actually independent of tau, or you may say it's a dissipationless. You can also do that, like in the anomalous Hall community. Instead of doing temperature as the variable, you can look at different samples, because different sample has different quality and therefore different sigma xx. And then you can basically look at the scaling as a function of sample number, and we can see that although the different sample have many different conductivity, they all have the same scaling, same anomalous Hall conductivity. Yeah. So I don't want to be over time, so let me actually just skip this. So then we can actually use this to measure the, as a function of the gate, because we have a two-dimensional device. So you can see that actually this nonlinear Hall conductivity changes quite dramatically as a function of the Fermi level. And this is basically, if you calculate the band structure, you see the quantum metric hotspots, and basically these peaks corresponds to the quantum metric hotspot. So it's we can say it's an energy resolved measure. So finally, we actually did a little bit of this wireless rectification. You can basically shine this wireless signal and try to measure the DC voltage that is transverse to the wireless electric field, and we can indeed actually see these kind of rectification, and we can also do that as a function of a frequency. We test up to, I think, 10 or 15 gigahertz. The spectrum is quite flat in this regime, although we only showed up to 6. Yeah, that's basically it for the experiment. So let me just discuss some future directions. So this quantum metric actually, at least from our limited knowledge, I think it's kind of equally fundamental, but less studied cousin of Barry curvature. And actually, but recently there are many theoretical works. So we study this nonlinear Hall effect, but there is a group, Gini Law. They actually study the superconductivity in the flat band system, and they argue that the flat band superconductivity in their system arises from the quantum metric. And as Martin mentioned, there's a very strong connection to the fractional Chern insulator and other kind of phenomena. So there are many, many things to do. And also, for the nonlinear Hall effect, there can be the quantum metric contribution, but there can also be other, skew scattering and side jump. Just like, if you're familiar, you look at the RMP paper of the anomalous Hall. There's this discussion of intrinsic skew and side jump. So now you can do this in the same way, but for a PT-symmetric antiferromagnet. Justin has a very interesting proposal that we're trying to study. And the other thing is obviously to look at these, try to understand this rectification and maybe collaborate with our friends in the engineering departments to look at this wireless rectification more. Okay. So let me just stop here and thank all the collaborators. So yeah, and take the question. Thank you.